Okay, this one is maybe a bit trickier because it consists in rewriting the code. So I want to do this using a loop somehow. So what happens so far is I have an array with as many elements as I have threads. And each thread puts its thread ID in the element that is at their IDth index. So if I'm thread 0, I'm going to put the value 0 in the element at index 0 in that array. Same for thread 1 at element in the index 1 and so on. So at the end in the array you want to get at the end in index 0, 0 in index 1, 1 index 2, 2 and so on and so on. Okay? So what we're looking for here, has anybody found a way to do it? Yeah, go ahead. Yes? Yeah. Oh, that's later. That's the parallelization of it. But first we need to get a for loop to parallelize. We don't have a for loop yet. I think you had an idea for the for loop? Yeah, go ahead. From what, sorry? Yeah, okay, for I equals 0 until... Oh, really? A copy paste? Okay. Okay. That's good. Did you make another change after this? It seems like a detail, but it's no longer a detail now. Why? Before I change this, in this case, we are always doing it such that if we have 8 threads, there will be 8 elements. So each thread is going to take 1 element. Behind the scenes, you're assuming, I guess, that, of course, if we all have to do 1 iteration, if I'm thread 0, I will do the first iteration. If I'm thread 1, I'll do the second iteration. If I'm thread 2, I'll do the third iteration. There's no guarantee for this. You can. By default, it's exactly what would happen. But you can change this behavior, which is what we're going to see, the last topic we're going to see today, how to change this behavior. So it's better to make it thread independent, just to say, okay, at iteration 4, I want the value, in the 4th iteration, I want value 4, well, 3 in this case, where I guess how you say it doesn't work. Value 3 in the 4th index, the 4th element. So yeah, let's put I. Equals I, okay. Fine. So now I no longer need my critical here. Do I need my barrier? Oh, first I should parallelize this. So as you said, yes, pragma OMP parallel 4. Oh, not parallel, just 4. Why not parallel? Because we already have parallel here. So we don't have to re-inject parallelism. Yes. Yes. In this case, you're going to see in 2 topics that in this case it's not going to help, because the starting point is each thread will be assigned 1 iteration. So even if you're late, we're going to wait you because your iteration, nobody's going to take it. There are ways to make that happen, but by default, it's not what happens. Okay, do I need the barrier here? No, I don't need it for a reason. So I still need to make sure that all this is done before I start to print it. Okay, we're good with this. It's just that at the end of the for loop, the parallel for here, there is an implicit synchronization. So the threads are going to split the work and execute the iterations of that for loop concurrently, probably simultaneously as well. And once they have all finished, they will proceed. If you finish your iteration, you're now waiting for the other threads to finish as well. So you have this free barrier at the end. Okay. 256 would be too much. Okay, since I have enough to type OMP num threads equals 4 every time, let's use the other version, export OMP num threads equals 4. Okay, now every time I run any program, I use 4 threads. Done. Okay? 0, 0, 1, 1, 2, 2, 3, 3. Cool. And done in parallel. Make sense? Yep. Okay. Let's proceed because we have 2 more topics and fun ones. So, reduction. A reduction is a clause in OpenMP. Do you know what reductions are? Simple sums, for example, reductions. It's when you're going to apply some computation, you're going to distribute the computation, calculate intermediate results, and then you're going to merge them, you're going to reduce it. Okay? So you want a result, you're going to have multiple threads calculating intermediate results, and you're going to merge that, you're going to reduce it in a total variable. Okay? So you have a way to express it in OpenMP reduction, which takes 2 arguments: the operation you're actually going to do, a sum, for example, and the variable in which we'll store the result. Now what's going to happen is, when the runtime is going to reach that reduction clause, every thread is going to create a local copy initialized to the neutral value to the reduction operation used. In other words, if you want a sum, every thread will start with value 0. Why? Because 0 is totally neutral to a sum. Something plus 0 equals something, so it doesn't change anything. If it's a product you're looking for, it will be initialized to 1, and so on and so on. You can also use it at parallel level, but so far we'll do it on a for loop, okay? But just to be complete, you can do it on parallel level. So, my little illustration again. I have a plus, so a sum, and I want to store the sum of all the local interactions into the original variable a at the end. So every thread receives a copy initialized to 0. They do their local calculations and somehow end up with these local numbers. They're going to put it back on top of the original one at a time, okay, plus 568, plus 1987. And OpenMP will also make sure that threads are not going to have race conditions, which is where they fight at the same time. We call that a race condition, you know, the critical and everything. So OpenMP is also going to guarantee correctness for this. And you may think, yeah, okay, that's nice, but that's only for a sum. Maybe I'm not interested in a sum. You're right, we have a few more operations available. And if you're still not happy, you can even create your own reduction operator, but that's definitely beyond the scope of this introduction session. Now, if we do this, so you have your original for loop, and you're like, oh yeah, I've seen we can use reduction. And then you may be wondering, where did the share go? Because they were shared here, and it's no longer here. Because when you're using reduction, OpenMP is treating things behind the scenes automatically. So you don't have to say if it's shared, private, first private. OpenMP knows it's a reduction variable, so it's going to take care of it in a special way. Because what I've just showed you is not shared, because they all have a copy. But it's not private or first private, because the values of the copies at the end are merged back to the original variable, which is not private or fast private. Normally, you're not supposed to interact with it. So it's a weird hybrid. So that's why just reduction, and OpenMP knows what to do with it. Don't worry about it. Now, sometimes you want to do reduction, but reduction is not what you can use. Probably a very confusing statement. Allow me to explain. If you're looking for some reason in your code to do a mix of min and max, for example, in OpenMP, you cannot say, oh, my reduction is min-max. That doesn't exist. Doesn't work. That's one case where you won't be able to use a reduction here. I will show you the alternative in a second, of course. Another scenario is, what if you would like to get the final result before the end? Remember this thread count plus that we had? And we had like a barrier and then a print? And you want to do something like this here? After the barrier, you would like to have a print statement. It's not working. Why? Because the thread that will do the print, when they will call A, they will just have access to their own copy. So they will show their own local result, not the final value. So in this case, reduction is not going to work either. Luckily enough, there's another way to do it called atomics. One more construct in your toolkit. Atomic is different from everything you've seen so far because atomic relies on hardware. Remember my little illustration with, okay, if I want to increment a variable, I'm going to read the value from the RAM, take it, locally increment it, and write it back. It's the fact that it's in 3 separate steps that allows the possibility of having another thread doing it at the same time. That's where it started from. As the hardware evolved and technology evolved, the hardware became able to do these kind of simple operations in one movement. So you just say, I would like to increment that variable in memory, and the hardware says, sure. So basically, you go there, but instead of going back to your place with the variable, you stay there, you increment it while you're there, and you're blocking any thread from doing it because you do it in just one move. So nobody can interrupt it. It's not like, I don't know, you are having a box of chips, like a poker chip or something, and you bring back to your place, you add one more chip and you bring it back. You just add it right when you're there, so nobody had time to somehow interfere with it. It's just one move. So in Fortran, Fortran at the bottom, of course. So the atomic, you just have to put atomic keyword, and then the operation assigned to it will be done atomically if it can. If you're trying to use an operation that the hardware does not know how to do in an atomic way, because that comes down really to what hardware can do in one move, the compiler will say, I'm sorry, I just can't do that atomically. That operation is way too complex for me to do in one go. You need multiple passes for this. So you'll need another way to protect it. Well, let's go with the reduction, and then we'll have the final schedule clause, which will be about optimizing your programs. So far, it's still about correctness. It's how to do something in parallel. So there's still the notion of performance here, but it's still how to do things in parallel while preserving correctness. It's still about correctness so far. What we're going to see the last module, now that you know, I think, all the principles, at least the essentials, to keep your programs correct in parallel programming, now I open you slowly to the performance side of things, the optimization side of things, which we're going to see with a schedule clause at the end. So, reduction exercise, and then move to the final one. Yes? Oh. Single critical atomic barrier, these may be clear now. They're very unlikely to be as clear in 2 hours or 2 weeks. So go through all that right now. So yours is between critical and atomic. Okay. Got it. Atomic, it's an abstract, semantic difference to begin with. Atomic protects an operation. Critical protects lines of code. Critical says lines 17, 18, 19, and 30, and 20 cannot be done by more than one thread at a time. Atomic says this operation has to be done in one move. In certain scenario, these two are equivalent. But constructs can allow you to do things that atomics can't. For example, you can have mutually exclusive sections of code on different data even, where atomic don't provide this feature. It's not what they are after. So you may think, well, then I'll just use construct all the way. Yes and no. You can use construct all the way, absolutely. The problem with construct is the overhead is not the same. A construct requires more overhead. Why? Why? Because they also need to think about mutual exclusivity. Is there another construct somewhere right now where I have a thread currently waiting or something? So this monitoring overhead makes it heavier than an atomic. But with construct, you can put anything you want in it. With atomic, you can use just what is currently supported. Your hardware can support a lot more than it was 10 years ago, but it's still limited. So, any other question? Yes. It's the compiler who would complain, yes, but the compiler makes this decision based on its knowledge of the hardware and what the hardware allows to do, yes. The part I don't know is how will it react if the atomic is not available. I think it's a compiler error that says I cannot make this operation atomic. Now, if it is available atomically, you don't have to worry about it. You can just compile your code and it will make use of everything possible. And when you start going into atomics, into hardware atomics, that gets quickly very fancy because you have many tricks you can use under the hood. But OpenMP will know all this for you. So you just bring your same code, even if it's a code that was written 30 years ago. You drop an atomic, or there was an atomic in it for ++ only. It will still work, maybe now using even more powerful techniques that actually may not be just ++. So that's the beauty of portability. You just take your code, you compile it somewhere else, and it will use all the features available without you even knowing what's happening under the hood. I'm not sure if it's the compiler that would give you an error message, or if it would be a warning, or if it would somehow try to let it go and fake like, no, it's okay, it's okay. I think the compiler would block it. Because if you were to run this program, I think the OpenMP semantics would be that the OpenMP standard is about the semantics. It's what assumptions can you make if you use this construct? What should you be guaranteed from a parallel point of view? So if you use atomic, then in your program, you are to assume that this operation now is done atomically because it's atomic. So you can use the fact that it's correct to have multiple threads executing this atomic operation. If this atomic operation was to not be supported, my understanding then is the compiler should tell you, I think, something is wrong somewhere. David, any idea of this? Oh, because I remembered, why do I tend to lean towards the idea of it will complain, and I think it should? It's because I encountered this with a compiler who just wouldn't allow me to compile because it said, I don't know this atomic operation. But then it was maybe a compiler-dependent behavior. Like this compiler was doing an extra work of saying, I don't have this atomic operation. And maybe now the common practice is for the compiler to switch to an alternative, which is typically constructs. But then if we start to switch to constructs, we get back to the case where maybe the construct they're generated, if it's the default name, it might now start to be mutually exclusive with other constructs in the code. So you see now everything starts to interfere. So it's quickly getting more complex. Okay, let's see the exercise 7 we said? Yes. So where are we up to here? Okay, approach 1, approach 2. So which approach did you use for the first one? It's okay, it's comfortable here anyway, I can stretch. Sorry? A reduction? Okay, let's go for the reduction. So, what did you write here? Default none, that's a good starting point, okay. And what did you put after that? Okay. And then what, sorry? Thread count, okay. I think we're missing an information here. Yes, we need the operation, yes. Now this one. So that's correct. The first one is correct. Thread count plus, yes. Now what about the second one? Because you've used your reduction card, now you have to use the other approach, i.e. We've seen reduction and we've seen another one. Which one is it? Atomic. So I'm just going to kindly ask the hardware to do this increment for me in an atomic way. Done. Simple. Every time I just have to drop one word. That's in MPI. If you know MPI, it's different. Really different. I love MPI, I teach MPI, but it's different. Okay, 4 threads, happy days. Now let's move to the final topic of the day. We have 20 minutes to cover it, we should be good. The schedule clause. So that works on loops. It's going to determine how your iterations are going to be distributed to your threads. Okay, so that's where you now start to have a lot of what we call load balancing to improve performance. There are 5 available. The first one is what's done by default. Okay? It's implementation specific, but what seems to be the default. So static, so that's how you set the schedule to static. You see 3 dots, it's because you have your parallel for something, schedule, and then static, and then a chunk size. So the way static works is you're going to take iterations and you're going to group them into iterations containing, you're going to group them into groups containing chunk size iterations, consecutive iterations. Okay? So if I have 10 iterations, 2 threads, and I use a chunk size of 2, I'm going to create 5 groups of 2 consecutive iterations. Then I'm going to distribute that in a round-robin fashion. So I give the first group, the first chunk, if I want to use the right word, the first chunk to the first thread. Second chunk to the second thread. Now I have 3 more chunks, but no more threads. Well, I take the third chunk and I give it back to the first thread. Fourth chunk, second thread. Final chunk, first thread. And you keep doing that until you have no more chunks available. Okay? If it was 3 threads, you were doing 0, 1, 2, 0, 1, 2, 0, 1, 2 until all your chunks are gone. So, fairly intuitive. By default, if you don't give a chunk size, it will be set to 1/n. So if you have 10 iterations, 2 threads, and you don't give a chunk size, by default, each thread will do 5 iterations, done. Okay, OpenMP will even take care of this for you, which is what has been happening throughout the session so far, because we were not saying schedule. So if you have 8 iterations and 4 threads, with a chunk size of 1, you have this nice pattern happening, okay? First iteration, first thread, second thread, third, and then you keep doing that. You repeat the pattern. If you change the chunk size, you give them 2 by 2. Now, look at what becomes a problem for performance, but still not a problem for correctness. If I move the chunk size to 3, first thread gets the first 3, second thread the 3 that comes after, and the thread number 2 gets the last 2 iterations, but thread number 3 gets nothing. So now in your code, you have generated a situation where one of the thread gets no work. So that code cannot get 4 times faster. Why? Because there's one thread that doesn't even do anything. So best case scenario, 3 times faster. And even that won't be the case. Why? Because the thread number 2 does only 2 iterations instead of 3. So it does less. So it's likely to finish earlier. So you see, the schedule is going to impact your performance. And when you're working on triangular matrices, all these type of complex workloads, that's exactly what you're going to start to focus on for performance once your correctness is taken care of. So what's nice is threads know in advance what iterations they're going to get, which means that the compiler has no work to do to keep track of who is going to do what. They know in advance. So the overhead of static is more or less nothing, really. The problem is, if you start to have load imbalance, where some threads, some iterations are much bigger than others, static is not very good to deal with these types of situations. Yeah. It's technically, you could tell me, well, if I do packs of 1 iteration and I give these chunks away, technically it could work, because then if the iteration cost do this, if I split it into little tiny packs of 1 iteration each, I should have a decent load balancing. And you're right. The load balancing will be better, but you've now destroyed cache locality. I won't come on about this today because it's maybe a bit too advanced. But if you want to know more about cache locality, I'll explain. But yeah, it's not designed for this. Dynamic has the same structure: schedule, dynamic, and a chunk size. The way it works is, let's come back to my first example. 10 iterations, 2 threads, and I group my iterations 2 by 2. Okay, so I have 5 chunks eventually. I start exactly like static. First chunk, first thread. Second chunk, second thread. I have no more threads. Now that's where things change. Instead of giving already the third chunk to the first thread, even if it's working, I'm going to wait. And I'm going to wait for one of the threads to come back to me and say, I finished, can I have one more? And I'll say, sure thing. So now I'm going to keep an eye on which thread is available, and I will give work only to that thread. So if a thread is super busy, it's fine. I'll just never give any additional work to it. So I'm going to load balance this way. If you don't give a chunk size, by default, the size is 1 in this case. So here, if I do a chunk size of 1, okay, for dynamic, I give first 1 chunk to every thread. And for the chunks remaining, let's say now it's the thread number 1 that came back first. Okay, you'll have it. Then, thread 3, okay, you have it. 0, 0 again, fine. Every time I have one thread that comes back asking for more, I give it more, okay? So it helps a lot. If it's dynamic 2, so if I give my iterations 2 by 2, I get the very same result than static in this case, because just with the initial round, I distributed all the iterations. So what's nice with dynamic is that it can really help you address load balancing with very little efforts. You just have to try maybe a chunk size, and that can get you to save a lot of time. But it has an overhead, because now the runtime needs to keep track of which thread is currently available. The threads need to come back, ask for more, so I need to keep track of which chunk I've given to whom and which chunk is next on the line. All this takes time, not hours, but still taking some time. And of course, finding the right chunk size, how many iterations you put in the chunk, that's not trivial. Okay, guided, I like guided. Guided is weird, because guided brings something new on the table. it says, okay, with static and dynamic, you have to pick a chunk size, and then you always make chunks of that size, which seems perfectly reasonable. But guided goes with, okay, what I'm going to do is I'm going to create chunks, but I'm going to decrease the number of iterations I put in every chunk so that the chunks become smaller and smaller and smaller. And you may be wondering, why would someone even do this in the first place? Try to think of triangular matrices, all these where the workload can increase, for example. So the first few iterations are very small, the last iterations are massive, and the iterations in the middle are getting bigger and bigger. By creating chunks at first with many iterations, you're packing a lot of light iterations together. And as you get to heavier and heavier iterations, you pack fewer and fewer of them in your chunks. So effectively, the amount of work per chunk remains the same because you have fewer and fewer iterations, but they get heavier and heavier. So you're doing load balancing here. Okay? The chunk size has a different role here. It's going to say, okay, do your stuff, diminish, reduce, decrease the number of iterations per chunk, but please never less or fewer than 5 iterations per chunk. So chunk size equals 5. Okay, so you're blocking the minimum size to make sure you're not at the end giving chunks that are way too small to make any improvement. And by default, it's 1. So guided is really good for all the triangular matrices type of processing, but it also has an overhead that is greater than static. So the way it works, I'll go through that quickly. It's going to say, okay, how many iterations do I have left? 0 to 8, so that's 9 iterations. Okay, how many threads do I have? 3? Yeah. Okay, so then I'm going to create a chunk containing 1/3, 3 threads, so 1/3 of what's remaining. 9 iterations? Okay, I'll create a chunk of 3 iterations. That goes to thread 1, the first thread, so thread 0. How many iterations do I have left now? 0, 1, 2 are removed, so I have 6 left. 3 threads? Well, I'll take 1/3 of what's remaining. 2 threads, and I make my chunk, and I give that to thread 1. I now have 4 iterations remaining, still 3 threads. 1/3 of 4, 1.3 something. Oh, I asked chunks to be made of at least 2 iterations. So 1.3 is less than that, so I'll make a chunk of 2 iterations and I'll give that to the final thread. Now I have some iterations to distribute, and all the threads have received their original initial chunk. The rest works exactly the same as dynamic. I'm going to continue making chunks, and I will give them to whichever thread is available first. In this case, thread 1, for example. Okay? Now, my favorite scheduling clause, auto. Why? Because auto just tell the compiler, I trust you, pal, you'll do a good job, go for it. You don't give any instruction, you have no clue what's happening, you cannot know what's happening, and it may do something even trickier than static, dynamic, or schedule. It may use something of its own, using fancy heuristics or something, but it's really a go for it, we're all behind you, and hopefully we'll do something good. So I quite like it. Easy to use, but you have to have faith, because, yeah. So if something goes wrong, too bad, you can't control it. You said auto, well, you told me I could do everything I wanted. If I did something terrible, too bad. And there's a final one, which is called runtime, because so far we have to give in advance if we want static or dynamic or guided or auto. Runtime says, use the schedule that I will tell you at runtime. I cannot tell you right now because I'm going to read data from a file. If this data has this characteristic, I know that static will be great. If it has that characteristic, dynamic will be great. But I cannot tell you right now because I haven't loaded the file yet. It depends on the user data. So there's a way for you to say, okay, from that point in the code, next time I want to use a schedule and I tell you runtime schedule, use the one I'm going to give you. So maybe OMP set schedule static 14. And next time I see schedule runtime, I'll be like, oh yeah, you told me it would be a static 14. Okay, I'll use that. Okay? So we're going to finish with this exercise where you have 3 for loops, I believe, that take a certain amount of time, and you have to find the right schedule to improve performance. This time correctness is done for you already, but now it's a matter of performance. Make that code go faster. Okay? Here you go.